this video, I'll be discussing how Bootstrap uses data modeling and coordinates planes and how these concepts are introduced to students. Modeling is an important concept of critical thinking and becomes especially important when students encounter word problems in which they must translate a written description of the system into a mathematical model of that system. After an expectation-setting introduction to the class in Unit 1, the students start out by looking at the Ninja Cat demo game. This is a very simple game in which the player controls a cat that is trying to catch rubies while avoiding a dog. The dog and the ruby move right to left, and the cat can move left, right, and can also jump. There's a cloud that moves right to left as well, and a score that changes as the cat acquires rubies or defeats the dog by jumping on him. If you're pressed for time, you don't have to let the students play the game itself. A simple 30-second demo is sufficient. The game is a simple system in which the behavior of each character is dictated by a set of equations. The first activity for Bootstrap students is a modeling exercise in which they break down the system into the simplest representation possible of what is fixed and what is variable. This exercise is broken down into 3 phases. First, list every thing in the game. Second, for each thing, describe what is changing. And third, think about each kind of change. What kind of data is used to represent it? The first phase is by far the easiest. Students will quickly list the cat, the dog, the ruby, and the cloud. You want to make sure that they'll also list the background, either as a single entry or as a list of things like, say, the sun or the mountain, and the score. The second phase requires that students think about what is changing for each of the items listed. The tricky part here is to guide the students to thinking in terms of nouns rather than verbs. In other words, don't tell me what the cat is doing, tell me what about the cat is changing. Most students will tell you that the cat moves, for example. Moving is an action, but what you're looking for is the position or the location as being the thing that changes. It's generally helpful to use examples for this. So for example, when you grow up, your height changes. When you get older, your age changes. Ultimately, students should realize that every character is only changing their position. The score's value changes, but everything else in the game is fixed and unchanging. The third phase is easy for students who've seen coordinates before, and you can jump straight into it by asking them to be more specific about whether the x, y, or both coordinates are changing for each character. For students who haven't seen the coordinates before, we introduce them by first talking about position in one dimension. Suppose you were looking at the dog pictured somewhere on the bottom of the screen, and you were trying to tell a friend on the phone exactly where the dog is. Is it on the left? Is it on the right? How far from the left? Ultimately, you'd want to use a ruler to measure the exact location of the dog from one side of the board. A number line. But of course, one number line only tells you how far the dog is from the left-hand side. One number just isn't enough to tell us how far a character is from the bottom of the screen. At this point, even very young students realize that we need a second number line. This establishes the coordinate plane, with the origin 0, 0 anchored at the bottom left-hand corner and the top right-hand corner being the top coordinate, 640 by 480. It's a good idea to have students figure out what the coordinates are of the other corners as well for practice. Once students have realized that all positions are coordinates, they can fill in the third column of the table. The dog, ruby, and cloud only need to keep track of their x coordinates, while the cat needs both the x and the y coordinate. And the score is a simple number. In total, that means the entire Ninja Cat game can be modeled using only 6 numbers. Now, for a lot of students, this is surprising, and it's worth going deeper by asking them how the data model would change if, say, we wanted the dog to move up and down as well. How many numbers would we need to add for 2 rubies? What about a 3D game in which each character can move in the X, Y, and Z axis? Finally, we end with, how many numbers do you think are used to model a game like Halo? At this point, students start to realize just how big a project it is to make a video game and begin to see how math comes into play even for something as simple as putting an image on the screen.